Folks, today we're going to talk about molecular polarity. Now, if you remember in the past, we talked about polarity and we said when we're talking about polarity, we are always talking about covalent molecules. We are not looking at ionic, we are not looking at metallic, we are looking at covalent molecules. And we've talked about electronegativity, and we said if the electronegativity in a bond was greater than 0.4, then we had a bond that was polar. So, for example, if we put carbon together with fluorine, carbon is 2.5 and fluorine is 4.0, so we definitely have a polar bond where the electrons spend more time with fluorine, so we get a slightly negative charge over by fluorine and a slightly positive charge over at carbon, as the electrons spend more time over here near fluorine and less time over by carbon. Okay, so remember that is the concept of a polar bond, where the electronegativity difference in the bond is greater than 0.4. The question is, how do we know if we have a polar molecule? Well, for bonds, we only cared about the electronegativity differences. But for molecules, we care about the difference, the electronegativity differences, and the shape. Because we can have polar bonds, but yet the molecule is not polar. And we'll give some examples of that. So, one of the things we look at is where is the center of the positive and the negative charge. So we look for those things that are slightly positive, the things that are slightly negative, and if they happen to end up at the same place, then the molecule itself is not polar. We'll talk about that. And why do we care? Well, polarity has a big impact on the boiling points of compounds. Specifically, if something is polar, it holds together better, so it does not want to boil, so the boiling points are significantly higher of something that is polar. So you should be able to figure that out. All right, let's look at a linear molecule. Right, if I have something where, for example, I have fluorine bonded to fluorine, well, it's the same thing, so there is no polarity difference in this bond. So where's my center of positive charge? Where's my center of negative charge? Well, it's right in the middle. So my center of positive charge and my center of negative charges are right here in the middle, where the electrons tend to spend their time. So this is not polar. But what happens if I simply take something like, well, let's say that I bond two things together like fluorine, and I bond it to chlorine. Well, chlorine is 3.0, and fluorine is 4.0. So clearly the electrons are going to spend more time over by fluorine, so that means fluorine is going to end up with a slightly negative charge, and chlorine is going to end up with a slightly positive charge. And you'll notice that they're different by more than 0.4. So that means our bond is polar, which means our molecule is polar. You'll notice that the center of the negative charge is over here by fluorine, and the center of the positive charge is over here by chlorine. So they are, in fact, in different places. Okay? So there we have a polar molecule. Now what happens if we have something that's linear where we have three atoms? Well, a great example of that is carbon dioxide. Carbon will doubly bond to oxygen, and this is a linear molecule where oxygen ends up over here on both sides. Well, carbon's 2.5 and oxygen's 3.5. So if this is 2.5 and oxygens are 3.5, then the oxygens are both pulling the electrons towards them. So I'm ending up with a negative charge on this oxygen, and I'm ending up with a slightly negative charge on this oxygen, but where's my positive charge? Well, it's sitting here right in the middle, right? So you tend to say, well, I do have a polar molecule. Well, in fact, you don't. Because where's the center of this negative charge? Well, I've got two negative charges. The center is going to be right up here in the center. So the center of the positive and the negative charges are in exactly the same place. So I do not have a polar molecule. Now, on the other hand, you might say, well, another way to look at this is, do I have a positive and negative end to my molecule? That's the way I tend to look at it, and here my answer is no. I have a negative end on one side, a negative end on the other, and the positive is stuck here right in the middle. So I do not have a positive and negative end, I have a positive middle. That doesn't work. Okay? Now, could I create something that has a positive and negative end? Well, again, if I put carbon in the middle, and over on one side I put oxygen, and on the other side I put something like let's say, sulfur, or selenium, or tellurium, then oxygen is 3.5, carbon is 2.5, so clearly these electrons are going in that direction, over to the right, and tellurium is 2.2. So these electrons spend most of their time in the middle. However, you really kind of have to look at the whole molecule as a whole, and since carbon's electrons are being pulled over towards oxygen, then carbon wants electrons a little bit more, so tellurium's electrons are going to be pulled over to carbon. So essentially I'm ending up with a slightly positive charge over here on the left, and a slightly positive charge, slightly negative charge over here on the right. So yes, here I do have a polar molecule. Right? Bottom line, guys, is as you look at this, if your ends have different stuff on them, then probably it's polar. But if they have the same things on them, then it's probably not polar. So let's look at something that's trigonal planar. And there's a perfect example where, again, you put boron in the middle because you have something that's trigonal planar. And now you put, let's say, chlorine out on the outside, and chlorine over here on the outside, and chlorine over here on the outside. Now, clearly, each of these bonds is polar because boron is 2.0 and chlorine is 3.0. So in every case, the electrons are being pulled out away from boron, leaving a positive charge behind. Right? So your slightly positive charge is at the center of boron, and you have a negative charge out here at each one of the chlorines. Well, then the question becomes, where's the center of the negative charge? Well, it's right back in the middle. So the center of the positive and the negative charges are right back in the middle. This is not a polar molecule, folks. And it's not because there's not a positive and negative end to the molecule. Right? Again, what you have is you have a positive center and you have a negative, you have negative ends. Again, if you replace one of these guys on the outside and you replace it with something else, for example, let's say that we put boron out here and we have, let's say iodine down here, and we have fluorine up here. Well, fluorine is 4 and boron is 2. That is almost ionic. These electrons are really being stripped out to fluorine. Now, iodine is 2.5. So you'd say, well, the electrons are going towards iodine, and they probably are spending more time out here. But realize that this is so polar that you're getting more of a negative charge over here. So I would propose that because you have different things on the ends of these arms, that I would say this is probably polar. But in all honesty, the usual thing you are going to see is something like this. Is something like BCl3 or BF3, where the things around the outside are the same. And in that case, it is not going to be polar. How about tetrahedral? Same thing applies, guys. If you have carbon in the middle, and you have 4 things around the outside, and they're all the same, I don't care what the electronegativity difference is, no matter how polar the bonds are, and these bonds are pretty polar. Fluorine is 4.0 and carbon is 2.5. So their electronegativity difference is 1.5. But again, where's the center of the negative charge? Right in the middle. Where's the center of the positive charge? Right in the middle. Do you have a positive and negative end to this molecule? You certainly do not. Right. So as a result, chances are this thing is clearly non-polar. But what happens if you change one of these guys from fluorine to something else? Well, it's going to be polar. You're going to say, well, wait a minute. Carbon's 2.5, and let's say down here I put 3 fluorines, which are all 4s. These are 4.0. This is 2.5. And let's say you put something up here, like a chlorine. You say, well, chlorine, sorry, which is 3.0. So you can say, well, I have negatives all the way around. Well, yes, but where's the center of your positive charge and where's the center of your negative charge? Well, your center of your negative charge clearly is going to be more in this direction because you have 3 things that are pulling down here at 4.0. They are very polar. So the center of your negative charge is closer to the bottom, which means the center of your positive charge is up here. Now, it's not completely end-to-end, but certainly there is more negative down towards the bottom of this than there is towards the top. So you will have a polar molecule. So again, with tetrahedral, if they're all the same, it is non-polar. If there's anything that's different, it's probably polar. And that's without doing any math. You can just say, oh yeah, it's polar. All right. Now what happens when you have a pyramidal shape? Well, you might have something, let's say like nitrogen up at the top. Nitrogen is 3.0. Right? And let's say that I put three things down here, and we're just going to say that that's fluorine. Or let's say, oh, let's be difficult. Let's say it's iodine. Right? So do we have a polar molecule? Well, bottom line, on something that is pyramidal, I can tell you that 99.9% of the time it's going to be polar, because up here, there's a pair of electrons just sitting up here. And that pair of electrons is unshielded, and they're just sitting out there. So you end up with a negative charge. So pretty much anything that you look at is going to be, any pyramidal shape that you see is going to be polar. Let's say you put hydrogens down here for NH3, this is ammonia. Two dots up there, this thing is going to be polar. All right. So if it's pyramidal in shape, it's almost always polar. So just go with that. For purposes of what we're doing in our class, just say if it's pyramidal, it's polar. And you can do the same thing with bent. Why? Because again, with oxygen, you're going to have two things coming off. With hydrogen coming down here, hydrogen coming down here, and now you've got two pairs of electrons up here. You can say, yep, that's going to be polar because these electrons up here are unshielded. Okay. So I'm not even looking at the electronegativity difference, right? And my electronegativity difference is significant in this case because that's 2.1. So my electronegativity difference is 1.4. So yes, the bonds are polar, molecule's polar. The center of my positive charge is way down here somewhere, and the center of my negative charge is going to be up here. Okay? All right, so if you see something that's bent or pyramidal, you can almost always say it's going to be polar. All right, so let's look at water. Let's just go back to water again just for a second, because water is always is something that is we see all the time. Hydrogen's here. Remember, it is a bent shape. You figured that out. This is a 105-degree bond angle. We have those two pairs of electrons sitting up there. So if it's a bent shape, it's going to be polar. What we have here is a video that demonstrates to you that water actually is polar. And when you have something that is polar, you can think about it, and it means that it would be attracted to a magnet. So here's an example of that. Here we have a little stream of water coming out of a faucet, and it's going straight down. And the purpose of this is to demonstrate that water actually is polar, that it has a positive and a negative end. So if I put it near a magnet, in this case a comb, that has static electricity, you can see the water actually bend towards the comb. Okay, I can put the comb on the other side, and it will bend towards the comb that way. So it is attracted to the static electric charge that's on the comb, and so the water, because it's polar, will move towards that. Isn't that cool? It works a lot better in the wintertime than it does in the summertime because you need more static electricity, but this is something that you can do at home. Show your parents, amaze them, let them know, hey, I actually learned something in chemistry. All right, how about CH4? Well, see if you can draw CH4. You're going to have to use the Lewis dot structure to draw CH4 and figure out its shape, and we'll go from there and then figure out if it's polar. All right, well, you should have figured out that CH4 is tetrahedral. Now, when it's tetrahedral and all four things around it are all the same, it does not matter what the polarities are. You can assume that it is, since everything around it's the same, it is going to be non-polar. So there's no question about this one. This is non-polar. Right, how about NF3? Pause the video, see if you can draw it. Polar? Non-polar? What do you come up with? Sure, NF3 looks like this. It's pyramidal in shape. You have 107-degree bond angles. And you have a pair of electrons sitting up here at the top of NF3. That's what's forcing these other guys down there. That means this is going to be polar. How about OF2? Cool, did you draw it? Come up with OF2 looking like this. Oxygen, fluorine, fluorine, a couple of pairs of electrons sitting out here on oxygen, unshielded, definitely polar. All right. Again, shape tells you it's polar. and you have 105-degree bond angles. How about SO3? Go ahead and draw it first, and then we'll go from there. All right. Should have come out looking something like this. That's SO3. And when you did it, you realized that you had oxygen all around the outside. You had the same thing around the outside, sulfur in the middle. Does not matter what the electronegativity difference is. You've got oxygen around the outside. This thing is non-polar. How about SO2? Again, draw it. Yeah, guys, you should be familiar with this because we did SO2 in the last podcast. But SO2 looks like this. And up at the top, we have that spare pair of electrons. That tells you that this is trigonal planar. So these are 120-degree bond angles. That was 120-degree bond angles. This is too. Right? But the difference with this is you have this pair of electrons sitting up there. This is polar because you've got the electrons sitting up there. All right, how about I2? That should be a gimme. That should be easy. This is iodine bonded to iodine. Linear, 180 degrees whenever you have two things bonded to themselves, and it can never be polar because they're the same thing. Now, if you had hydrogen bonded to iodine, definitely polar because they're different. But I2, no, definitely not polar. Let's try HCN. So you can do that one. Right, we've got H bonded to carbon, triply bonded to nitrogen. Again, guys, I'm not even you don't even have to worry about what the electronegativities are for these things. Right? Your hydrogen's going to be 2.1, carbon's 2.5, nitrogen is I don't even remember what nitrogen is. I'm guessing it's around 3. Right? Bottom line is you have different things on the ends of the molecule. It's going to be polar. The electrons are going in that direction. So you're going to end up with a negative charge on this end and a positive charge on this end. It's definitely polar. All right, folks. You should be able to look at a bond, and having an electronegativity table with you, we will give you the electronegativity table, you should be able to tell whether a bond is polar or not. You should be able to draw the molecule based on the Lewis dot structure and then figure out its shape. Based upon that, you should be able to tell me whether the molecule is polar or not. And then you should know that polarity does things like affect the boiling point. The more polar something is, the higher the boiling point because things are held together more. All right, that's it. If you have questions, see me in class, and I'll be happy to help you. All right, have a great day. Bye-bye, guys.